Okay, thanks, Professor Nagesh. It's my pleasure to attend the Optical Sensors Clusters monthly webinar series 4. It's my pleasure to share our work, recently work-based about portable optical fiber sensors integrated with smartphone for healthcare monitoring applications. This is one of our main research area in recent years. My name is Rui Ming and from Beijing Normal University. And just as Dr. Nagish introduced me, my name, I get my PhD in University Bolívar de Valencia, and now is associate professor in Beijing Normal University, and this is my research area, and some work for this community, and due to Dr. Nadish is already introduced, so I just skip this page. Um, Today, my presentation is divided to five parts. First part is about why we want to do this portable optical sensor. This is the motivation to do this. The second part, I will introduce the basic technology for this kind of sensors. The third part I will introduce about for specific application like cardiorespiratory monitoring, and then I will introduce another some of our work about for gauge monitoring, and at the end we will do a conclusion for all this. First is the motivation why we want to do this. Actually, as we know that in the world, populations are getting old. You can see this from the right graphs, from the left graphs. You can see in the 2025, there are for the age more than 16, you can see for the blue colors, they are 30 and more, and a lot of them is at the 10 to 13%. So now population aging is already a global issue. So what we can do to do this, well, to help us to when we are older. So now what we want to do is about for center monitoring systems and some television telecare provision, physical to do some physiological information monitoring for the elderly. If we want to do something like this, we can do something. We can make it wearable. A wearable sensor can be used for this kind of things. And the motivation for mobile sensor in recent years, first is that the foundation of the next generation of personal medical device and remote medical treatment. We can monitor heart rate, pulse wave, body temperature, and blood pressure. And also now the information technology is growing very fast. We can build a personal centered health system. Also, as you know that AI technology that like DeepSeek and a lot of things can explain the application of things of scenarios of the wearable sensing devices. We can make it how can I say more famous, such as that human computer interaction or some or interaction with the environment. Also with the material due to the material technology growing, so we can use a lot of soft material to make such sensors. Before in many years, a lot of electrical sensor is a very good kind of sensors, and it can be also it is now very commercial. It have a lot of benefit, but for some specific application, there have still some problems for physiological monitoring, such as that the electromagnetic field interface and the electro chemical correlation. So we want to do some research about to solve these problems. So our aim is to focus on optical fiber sensors. As we all know, optical fiber sensors still have some problems needed to solve to go to commercial. So that's why we still do some research on this area. Many actually silicon optical fiber sensors is based on silicon optic fiber, and silicon fiber is commercial and it, as all of guys you know that now the worldwide internet is have the benefit of silicon optic fibers, but it for the specific application like physiological monitoring, it still have a lot of problems such as its strain range is very limited, the quality is brittle and easy to break, and make it to break may cause potential may will damage our body. So what do we want to shift our air to polymer optic fiber. Polymer optic fiber, as you know, is based on polymer. Some specially polymer have some specific application, specific performance like biocompatible, low elastic modulus, and has excellent human compatibility. This is a very good candidate for physiological monitoring as wearable sensors. This is the main motivation why we want to do this for portable the optical fiber sensor. Also, why we want to do portable to make it wearable. Now I want to introduce the basic technology of this kind of sensors. This is actually the page of the material of this page is based on the review paper we published last year on biomedical optical express. We at this review work we call this kind of sensor like optical fiber biosensor integrated with smartphone. Actually, this is more or less the same. And but in this review work, we divided to chemical biosensors and for physiological biosensors. Physiological biosensor is more related with what I want to introduce today: wearable sensors, portable wearable sensors, and this is for application. And for the structures, for technology part, it need as we know, all knows, for sensors, we need a hardware, we need the integrate technology and the sensing method, sensing technology. So for the hardware, because we make the portable, so hardware we include optical transmitters, optical fiber, sensing structure, and the photo detector to detect the night variation. And for the integration technology with smartphone, we need a bracket. Also the multiplex pathways and also some data processing software technologies. And for sensing, due to that now, two main is that we detect the intensity change. We also detect the spectral change. This is now the main two technology we explored. This is all this like the left flow chart says, and the overall framework is like this. And in the right part, this is a typical hardware combined for a portable optical sensor integrated with a smartphone. As you can see that we have a smartphone here, and we use 3D printed connectors to connect it with optical fibers, and for we use flashlight to be optical transmitters, and we use a photo detector of the camera of the smartphone to detect to detect the light change. And due to that, we wear it on the body, and we need a sensor structure. Here we use PDMS, PMMs, elastic materials to make them more sensitive. This work we will introduce in the next part, more detail. And here I want to introduce some selected hardware combined for portable optical sensor integrate smartphone on the different studies. This is literature we collected in recent years for this similar for these research areas, such as from 2017. There's one research group use polymorphic fiber and multimodal polymer for based on transmissive uh, uh, transmissive station and use with your smartphone to to be to detect your but here it is not mention how to detect what, just use the basic technology. You can see from in this maybe I think is to now is around 8 years. Is the technology is changing to from the optical transmitters to optical fiber and to sensing structure, also the photo detectors. And in the left part, you can see the real picture, the picture of the smartphone, and also the structure, also the typical blanket design. This is the two night transmission path design. As all of you know that you optical fiber want to be a sensor, it have need to have a sensitive area. So you can see in the central part of that left pictures, you can see we have a sensor structure change as the figure B. Just like we polish it and we put some materials on this part and we cut it to make it sensitive to the light change wave various. This is the sensing zoom. And for the data processing now we need to, because we get from the we- due to we use that smartphone, the camera to get the information. So all what we get will change it to a picture. So from video to picture, so we will do some data processing flow chart to change the, just like here you can see first we get the video, we will do the pixel data acquisition, then we will frame by frame conversion this video to a grain scaled pictures, then to extending use singles to do some single acceleration to do some just like to wavelength change or intensity change to get some special frequency to do something like this. This is the main data processing flow chart. And after and this page we will main focus on the application, because just in that page we didn't mention about the application here. We want to we conclude some literatures about only on application, just for breathing rate application, human gait application, and also cardiorespiratory and pulse wave. All this is based on the optical fiber biosensor integrated with smartphones. And what we do is all based similar like this to do some breath rate, home rate, and post wave we will introduce later. And after the basic technology introduced, now I want to introduce several works based on our in our group recent years. First is about for cardiorespiratory monitoring. First work I want to introduce is one work we published. I think is in in 2021, almost 5 years before. This is the first work we work on this topic. Also, so it is a bit simple. So you can see from the left uh, graph, you can see that this is the schematic of the Propeps system. You can see actually this is like the one we presented before. We use a smartphone and we use a 3D bucket and we use optic fiber to in your breast near your breast, and we get the video, and you can see here is a white point, and this white point will change, will varies the intensity due to your breathing. So we get this video to into the computer and the code, and we due to some software technology we can get breathing rate and heart rate. This is the main idea. And in the right part, this is the CC area fabrication. This is a very normal fabrication method. We just cut the optic fiber, and you can see in the D we cut in 3 point. to make it more sensitive to your body change variation. You can see some light where change get out. You can see from figure D. And this in the left graph is about the light intensity single changing. We use different band pass filters to get the with different frequency. As all of you knows that heart rate and breath rate which have specific range. So we use a different range to connect to different singles, and we to change it to time domain and the frequency domain. In the frequency domain, we will see it very easier to see it. And before we do connect to singles, we do a pre-experiment to make sure what we can do from this. We just use a flashlight, a scrobable stick light source. We change it to the intensity change or we shut it. So you can see with a frequency, you can see, so we can get the frequency easily. This is just to make we make sure what we do is in a right way. Then we write this kind of sensors on the body, and and as we can. This is also one part we design with one sensitivity regions, also two sensitivity regions, and three sensitivity regions. You can see from last graphs here. Here is have three sensitivity regions, and we why we want to do this? We just to want to make sure that the three sensitivity regions we can get a better result compared with others. You can see from the last graph from here, the result is much better compared with previously with single sensitivity zooms and two sensitivity zooms. And we also to do some analysis about some for the shutter about for the software in the smartphone for the camera, such as that the shutter speed or the something others. Also, you can see from here. Also, this is in the left graph, and in the right graph, I also introduced just about the singles of with different frequency, different time corresponding to respiring rate. And then for the application part, we also introduce we also do some analysis about with different motion states. We will try to running or to working, to standing and sitting and square, just wear this kind of sensors. And this is the time domain singles, and here is the frequency domain. And from frequency domain, from the physical domain, you can see we can get some conclusion that the maximum power of heart rate varies greatly in different states, which can be used for infer the motion state of human body. At the same time, depending on the frequency, it can be used to infer the intensity of the exercises. This is the first work I want to introduce. And then, based on that work, we in the after 3 years, we did another works and to enhance this work. There are two. Actually, this is me as well. This is based on the work on the work we presented before previously. And here we improve the two parts. The first, the one innovation point is that in the sensing area processing diagrams, we just cut the plastic optic fiber. Actually, this is in my mind, this is not a good method, and the repeatable performance and a lot of things is not so good. So we want to also the elastic performance also not so good. So want to solve all these problems. So we found a new method to do this. As you can see from here, we cut the normally plastic optic fibers, and we use a elastical tube to make some PDMs inside, and we insert two in both sides, and then we thermal curate. Actually, this method is maybe you can see it is very easy, but it will just in one with one step. You can combine these two kind of two optical fibers. But if you don't do research on this area, maybe you don't know that for polymer plastic fibers, it's very difficult to do the bad coupling. Now we use the silicon tube to make it look like a optical fiber, elastic optical fiber, to combine all two of these to make it easy to coupling. Also to make it have a elastic performance, to make have improve the sensing performance. This is one of the main innovation part of this work. And the right proper schematic system is almost the same as previous. So I didn't do some introduce. Apart from that innovation part, we also did one work. We use a 3D improve printed mode. Yeah, is this put in the before your chest. Why we want to do this? Because that actually this is also a very easy idea but no one did this before. We use this to make it to more stretch of the optic fiber, and to make it more sensitive to the body. Also, we do some mathematical certificate. This is a correct idea, and what we want to say, we improved the quality of the light singles and make it also. This is also to improve the sensitivity. And then in the left part, in the right part is similar as before. This is a video, and we do we achieve the relative light intensity singles, and we use the bandwidth pass filters to filter the singles, and to get the respiring and get the heart rate singles. And we also to do the left part is just to demonstrate we didn't know the importance of the 3D mode. This is, as you can see, if we didn't wear in the 3D mode, the peak, the intensity will be weak. But if we wear it, we demonstrated with, I think it's around 10 people, and with a lot of experiment to get these graphs. Also with male and females. And also in the right part, we also demonstrated that the sensor we presented in the 0 months, and after 2 months, you can see, of course, it changes some peaks, but it's more or less the same. And even it be more stable. And here in the left graph, this is about in the figure A. This is the real graph we achieved, and we get then in figure B is the frequency part. We get it from here. We can know the frequency of the cardiorespiratory, and in the figure C and figure D is a time domain. And we also, as I mentioned before, I asked a lot of people to attend to this experiment. So we will also do the beta Altman analysis to make it to the reproduce performance of our sensors. The results indicated all of with 15%, 5% confidence intervals, indicated that this device can have a high monitoring occurrences. And this work, we also did the HRV monitoring. From the single we get, we also do some application for sitting fast, breathing, walking, running, to achieve the HRV for different states. And the results indicate that the device can detect HRV in different wavelengths. The right part is the results for this. You can see SDNS MMs is good. And this is the two work I want to introduce for this part about cardiorespiratory. After cardiorespiratory, so we also want to do some another applications. We cannot only do this kind of applications. So we want to do we have one idea to do for gauge monitoring. you can see from here we improved because for gains it is a little different. You because for the heart rate maybe you have one sensitive area you can it's okay, but all you know that in the plant you have different sensitive different areas you can see. So we use three so we improved all the designs. We usually use three channels of optic fibers to have. You can see from the left graph you can see here how in the six you can see here we have three white point because that these three white point is represent the three different areas of your food. For blender you can see in the right part figure A you can see for sensitivity 1, sensitivity 2, sensitivity 3, and we integrated all these sensor in a shoes in the real the picture as figure B see you can see this is the real pictures, and in the figure C you can also see the sensing zooms. We integrated to this, and in the next this is due to we have now the single processing is much difficult than previously. So you can see we make it you can see we first we get this video and we split image singles. We extract one of the images, and we also do some image to denoting such as threshold setting, flip filters, and we use one method. Here we use Voronoi function to get in the center of gravity. Use the region props functions, also the generating variant diagram by Voronoi functions. Then applied to all of these images, we get a multi-channel, single channel frameworks. The picture you can see in the left part. All what we want to do, just we want to spread this channel to for channel because we need to analysis. We cannot to connect the analysis all this at the same time. Then this part is more or less similar as before. We do the frequency domain, time domain. We will do the frequency change. But as this one is a little different, different as before is that the we didn't do a lot of frequency filters because that as you can see for cardiorespiratory you have a specific range, but for gain normally we don't have this kind of things. Here we do the PSD analysis, time domain analysis. We also do some for single sensor test, multi-single test, just to demonstrate the sensor performance is good. Here we will do some pattern real. We will do one pointers were the sensor we designed, and this is the result what we achieved. The Blender spatial change diagram in the single gain circles. The average gain circle wavelength diagram in swing phase and stretch phase, as the left graph shows. You can see. And in the left shows we ask a different guy several monitors to work our sensor to make our sensor is it's not for only for one guys. It's okay for different kind of monitors. We ask the six monitors to work our sensors. This is the result we achieved. You can see the frequency we get is clear for different guys, and we as all of you knows that this kind of sensor we designed by ourselves. So we use a commercial electrical sensors to calibrate our sensor to make sure what we get is correct. And this is the electric sensor we use to calibration in the left graph as you can see, and in the right part you can see this is the result. From this graph, you can see that the sensors and the first data we get from these commercial electric sensors is more or less in the same straight. So this is just demonstrate the performance of the sensors, and in the here we also do the experiment. This is, you can see here have one guy to work our sensors to working, and with three different sensor is change vary because it is in the different area of the planters. And here is the result of what we achieved. You can see here for running, for working, for running, for jumping, it is very easy to get the singles. You can see from here. And we also we standard or we change some things. You can sit, stand. You can see we do all of this kind of experiment to make sure to demonstrate the for the real the secretarials of our working or something or for real applications. This is the first work we demonstrated we do for Gantt monitoring, and I think this work is published in 2 years before in Archival journals. This work in 2020, this the work I just introduced, and then in 2024, last year, we improved these structures. Also, you can see in the left graph, we also write we get a nice graph for this idea. We increase we make it more how can I say more visible, making them the graph more good. And you can see from here in the right part, we call this as SFSPOV, Intelligent Insurance Sensing System. Actually, the main idea, the basic idea is similar, but we improve a lot of things. I will introduce you now. You can see from here, we use also use the three channels, and by the way, use a real-time transmission. And to do some active, we also introduce a lot of network in the narrow network here in this work. I want to introduce more. And in the left graph is you can see this is a smartphone, this is the bucket, and this is the shoes, and this is here we use we didn't use the sensing area is changed a little. We use similar we use also the elastical tubes, and but we didn't then use put a lot of we just put just the inside we don't leave the empty inside. Why we want to do that? Because that here we want the pressure with this kind of structures. It is the most sensitive to the light, and you can see from here this is a little different. The process is similar, but the structure is a little different. The process, as you can see from here, we mix the also we use the Solaris. We didn't use the PDMs. We use the Solaris elastomer procedures with a one weight radius, and we inject the mixture into the elastomer tubes and insert the bare pop core and query at the room temperature. And the picture you can see is in the figure E. This is the real picture of the structure. Then did a very detailed analysis about the performance this kind of structures. We did the such as the bare pop length test with intensity change or elastic different with different elastic length change. Why we use this kind of length? And also we use different materials compression. We use Solaris, we use Dragon, we use Syncret 184. All this kind uses elastomer materials. We just to see which one is better. And we also to do the durability test. We do maybe we test this 1000 or performance to see what something changing or something. We also do the bending response performance. Also, we put it in the water in area and to see the light ambient light resistance and the temperature influence performance and the pressure response test and the ground truth compression. We did what we in our mind to do the test to make it more the readers know more about what we did the performance. Then we improved that this one is similar, but we do some improve just like in the first we did the transmission video to the PC. Then we convert it into a gram matrix and adaptive stress to for images segments and grayscale matrix summary and single processing. Here with a Welsh structure spectral analysis to get the data and. This is the for picture. Here is the analysis of Gantt phase. You can see from the left graphs, we this from the A and B is experiment we design just like we do a round in 3 minutes, three sounds limits. I think it's 3 meter limits. We also did a stand, sit, and to go around to go around in a 2 meters circuit. We also in the figure B is that a different stage when you are working. Just like here, ground contest foot, 4 foot ground contest here off the ground, and the tour of the ground here round contact. We just to demonstrate the different stage. We also to do the some experiment like in figure C, like we working, we running, we turn left. Here we add some experiment like turn left and turn right. Before we didn't do such a kind of things. And sit and stand. This is the amplitude of the 3 channels of we get in figure C. And from this graph, we can get the experiment. We get the result is that for straight phase is 15 to 0.5%, and for swimming phase is 15 to the 0.5. This is for people is okay. And here we did a detailed analysis about to go turn right, turn go straight, turn left. You can see from here, you can see that analyze different grand patterns. From we can see that the average intensity of the 3 channels in the case of working and for different running and for turn left and go straight and for turn right, the intensity is totally different. From this, we can analyze what is the situation we did. And here we use try to classification for Gantt patterns. We introduce a lot of AI technology, just like decision trees and different classic models, random forest, K, nearest neighbors, spoiled vector machines, based neural networks. We try all this kind of method to see which one is a good one. We also after try we use RNN to for enhance the classification, because we find that some of this kind of method is not so good. And for RNN, we can get a good where compared with others, it's much better, and we get the result. Average predicting accuracy for each pattern is like for work we can get more than 55, and for run we can get almost the 100% of a stand is more than 55% for seed. All these kind of results, except one, you can see from turn left it's not so good, but others is also good. So we want to solve these problems to improve the quality, improve the accuracy of turn left. Then we did other work in there. Here you can see here. This is the next part. We use RNN for enhanced classification. Before we didn't use RNN. I just sorry, I have a mistake. Before I say I will use NN, but here we use RNN to enhance this. And we after we use the RNN, this is the right part is the result. We after we use RNN. Here also have some structures, internet resonate or network structure enhanced one. And after we use this, we can get turn left to be evaluated to it will be much higher. You can see from here it's only 55%, and after we use this, the achieved to get more than 55. So with this classification, we improved of 16.6 compared to previous accuracy levels. This is in our this is a good thing we get. And after this is the work the second work we for Gantt monitoring, and the last work I want to introduce is I want to combine the gait and cardiorespiratory. And this work is in this year published in IEEE Internet of Things. This is also one journal supported by our sensors console. And this is the schematic of the health monitoring system. We combine all the cardiorespiratory and gait to all this. So we get a four channel. One channel is for cardiorespiratory, and three channel is for the grant. Here is a optical fiber part. We use a polished optical fiber, and this is in the left part is the image of the phone on the receiver, and the night I introduced this before, and here we do a schematic like a image image single processing and real-time monitor video to smartphone. And we also use a mark operation, several agglomerations to create square images segments and to different label with for different labels. This is a different method as compared with previous ones. Also, we did the data flow chart. You can see data accuracy, baseline remove, and noise remove, and sliding window segments, and normalizing all these singles. And here, because that we do that calorie pairing, so we use but different filters for this kind. And you can see only for the calorie pairing, we wear this kind of sensor on the body. You can see we can get in the part. You can see here we can get the time domain and the frequency domain. We can get the results good. You can see from here. From you can see only one white point here in this page. This is only the one channel for the cardiorespiratory, and the other channel, three channel is for you can see from here for three sensors. Here you can see. Actually, this is more like we combined these two kind of work before. This is also similar that we do the walking, running, jumping, standing, and squaring, and we do some AI classification. You can see it is very good. And I think this is the main work I want to introduce here. And the conclusion is that the aim is what we want to do is only is for the physiological information monitoring for the elderly, for gait monitoring, for R combined, and for HR monitoring. And this is what we do. And I want to introduce thanks to our partner, our thanks to our funding agency, and thanks. Hope it's not so boring.